Hello, my name is Abdul Al-Katani, and I am part of project 21076, titled Smart Silo Design for the Safe Storage of Combustible Materials. My team members are Andy Kamarowski, Francisco Martinez, and Gassan Fimban, and we are all chemical engineers. Our mentor is Dr. Farhang Chadman. Combustible materials such as coal, silage, and ammonium nitrate are commonly used in agriculture and industrial processes as fertilizers and mining explosives. Storing combustible materials in large quantities and in relatively hot conditions, accompanied by weak mitigation and temperature regulation measures, would lead to the formation of hotspots and an increase in temperature of the material, leading to an explosion. A recent example of large quantities of stored combustible materials exploding was the unfortunate incident that occurred in Beirut, Lebanon, August of last year, where large quantities of ammonium nitrate caused a massive explosion due to storage in poor conditions for an extended period of time. Another explosion that involved large quantities of combustible materials stored with no adequate combustion mitigation was the incident that occurred in the West Texas plant, where 270 tons of ammonium nitrate combustion resulted in fatalities. Had mitigative measures been properly implemented, those explosions would have been less severe or completely prevented. The aim of our project is to design an autonomous smart silo that monitors temperature changes within the storage unit containing the combustible materials and maintains the temperature within the safe operating range.
So right now we're showing our overall process flow diagram of our smart silo system. The way that it functions is that at stream 8, we have air coming from the environment going through our membrane dryer, being dehumidified, along with our stream 1, which is our recycled air. As that air is dehumidified, it goes through stream 2, which then enters our centrifugal compressor, where it's compressed and then pushed out through our stream 3, where it passes our valve 1. Our valve 1 is actually controlled by a computer, which as it monitors our temperature thermocouples, 1 through 4, it regulates the amount of air going through the system. As the air goes through stream 6, it passes through the silo at a ratio of 10:1. So some air does go through the material. They're just meant to dry it so it doesn't clump. And that air exits through stream 7. The rest of the air goes through the piping in order to cool down the material, and that air is recycled through our stream 1. And then we also have our nitrogen cylinder tank, which is for any emergencies that occur within the silo in the sense that when temperatures go up.
There are equations for the heat dissipation and generation in our simulation. For generation, we combine the mass transfer, which comes from the oxygen moving through the air to the surface of the solid, and the reaction rate, which comes from the values for the specific reaction. In our dissipation, we use the convective heat transfer coefficient, which we get from a correlation using the velocity of the air in the pipes. For our mass transfer, we use the Sherwood number with a correction for countermolar diffusion from the gas produced from the combustion reaction.
Onto the heart of the project, our heat transfer simulation model. Using the aforementioned heat equations alongside secondary ones, we modeled heat of generation versus dissipation in the silo storage unit, as you can see in the figures above. Now, these model heat transfer for carbon-based silage at different purge gas velocities, and safe operation temperatures will be different for other combustible materials depending on material-specific parameters. Whenever QG, heat of generation, is below QD, heat of dissipation, the system is under safe operating temperature. And using the model, we determine the overall safe operating range for that specific material. When our thermocouple detect exceeding rates of temperature increase, the flow rate of the dehumidified air required to bring down the temperature back to safe conditions is also determined through our heat transfer model. And all of this is executed by our autonomous computer control system.
In our computer control system, we first measure the temperatures from each of the thermocouples. We then find the highest temperature amongst these and use this to err on the side of safety. We then take our inputs, including the airflow rate, the compressor's on-off condition, and rather the nitrogen valve and compressor valves are open or closed. We also take in the values inputted for reaction-specific values. We then use these to find the solid temperature when the heat of generation is equal to the heat of dissipation. If this TS is greater than the highest temperature, then the operating conditions are safe, and this calculation is done repetitively until a discrepancy is found. If TS is not greater than the highest temperature, then flow rate is increased. We then recalculate TS and continue this process until we reach a point where the TS is greater than the highest temperature, or increasing the airflow rate is no longer possible. If increasing the airflow rate is no longer possible, we then enter the emergency mode, in which compressor is turned off, the compressor valve, the nitrogen valve is open.
So to conclude, our goal for this project was to create a smart silo to store combustible materials. And for that, we wanted to make this usable for multiple materials that are stored within the silo. And one way we figured to do this was to make it material specific parameters that can be changed depending on the material within the silo. One of these parameters is the activation energy for the reaction. The other one is delta H, or the change in enthalpy of the reaction, and A, which is the Arrhenius pre-exponential factor for the reaction. All these three factors can be changed based off the material within the silo. And then given these values, we want our computer model in order to make these calculations, in order to find what is our safe operating temperature, and also to determine the flow rate necessary to keep our silo within and below that operating temperature so it doesn't combust. And then we also have an emergency tank, which is there just in case our temperatures within our silo do go above our max temperature operating, we can cool it down and purge it. Thank you, and I hope you enjoy our presentation.